Hi, everybody. Title of this presentation is High-Speed Sensing of the Electromagnetic Environment for Cognitive Radio Receivers. It was a multi-group project between Aspen, Columbia Integrated Systems Laboratory, or CISL, and Peraton Labs. So just a brief outline. We'll just have an introduction, background and motivation, some that we're all familiar with, cognitive radio applications. Our proposed solution, one of the components of our hardware system, the EMEA sensor, a couple slides on that. We'll go over the hardware, then the machine learning based decision engine, and then we'll go over some future work and conclusions. So I'm sure we've heard a lot about it. It's our field. EM environment is cluttered in multiple domains: frequency, time, angle, makes reception with an outstation increasingly difficult. The current detection methods now are not scalable if we consider all the possible places in the EM environment that we can find white space in. So we present a receiver architecture that uses compressed sensing to sense an emitter's location and also sends that result to a machine learning based decision engine to come up with the optimal decision for the transceiver to retune to. So this is just basically a graphical description of what I just described. We could see here two bottlenecks. We could see an n-dimensional resource cube of the EM environment, frequency versus time, frequency versus direction of arrival, quality of service, or burr could be another one. We could also break it down further: modulation characteristics, other more internal characteristics of the signals. And then once we've identified the signals and where they are in the EM environment, we need to take some sort of corrective action. So there's also another bottleneck on the possible transceiver actions. So for the sensing problem, oh, I'm sorry, I'm getting ahead of myself. But the device that we propose is called the ITRN, the Intelligent Transceiver Radio Node, to sense and come up with the optimal decision to use. So this is just a broken out block diagram of it. It has a few parts. It consists of an EMEA sensor, which stands for EM Environment Aware Sensor. And then it has a transceiver that's communicating with an outstation and a machine learning based decision engine. You can see here, just in panel B, what exactly is happening, and we have some signals that are incident on the antenna. We sense them using our EMEA sensor very quickly, take the locations, send them along with a quality of service metric of the outstations to the MLBDE, which then comes up with the optimal decision for the transceiver to take. So we break, what we do is we exploit a characteristic of the RF spectrum called sparsity. So assuming that the RF spectrum is sparse in some domain, in this case the frequency domain, meaning that K signals is much less than N possible signal locations, we can use a DSP technique called compressed sensing to drastically reduce the time it takes to perform a scan. And on the back end, we use reinforcement learning to make this optimal decision once we learn the spectral locations of the signals. So we use a custom piece of hardware that we built and actually presented at RFIC 2018. We won third place. Basically, it's called the DSIC, the Direct Space to Information Converter. It breaks all the trade-offs between resolution and time and bandwidth that either an FFT-based spectrum sensor or a SWEP LO or a channelized spectrum sensing technique uses. Instead of using N measurements for N possible signal locations, for instance, like an FFT or a swept spectrum analyzer type of sensor, it uses M equals to K C0 log N over K, where K is the number of possible number of signals and N is the number of possible signal locations. So like I said, the direct space to information converter is used as our EMEA sensor. It's an 8 antenna RF ASIC built in TSMC 65 nanometer. And it's already been published and used for spectrum sensing in a spatial domain, or angle of arrival. So when it's put into spectrum sensing mode, we could take a look at a couple of PDPFA curves. So we could see here for one signal at minus 55 dBm incident signal power, we're able to get 90% probability of detection. And for up to k is equal to 3 signals, using 19 measurements and 4 iterations of orthogonal matching pursuit, which is what we use for the compressed sensing recovery engine, we're able to recover with 90% probability of detection at minus 60, minus 55 dBm. This is just a block diagram of our hardware prototype. We use an EDIS X310 with 2 basic RX daughter boards and 2 DSIC chips. For the demos that you'll see in this video, we're using only 1 DSIC chip for 1 band, but it does support 2. We need to use a sync pulse to synchronize the DSIC chip with the EDIS X310 for just data framing. And that required us to do some manipulate the FPGA a little bit more, which Elliot will talk about now.
Right, so to get this working with GNU Radio, we wanted maximum throughput, and we didn't have a very high dynamic range requirement. So what we did is we took 7 bits of IQ data from each analog channel and packed that into one 32-bit vector that includes the sync signal. So we can get, so essentially we're kind of doubling the throughput by just using less data, and also putting in that sync signal so we can do the recovery properly. So started with the UHD 3.15 release for the X310. And then most of the changes were done in what's called the knock block DDC, which contains DDC for each analog channel. So there's 2 of these for 2 analog channels. And essentially, the solution we came to was each DDC would share its IQ data with the other DDC, reformat the data, like in the previous slide, put in the sync signal, and that way we could use only a single AXI interface from just a single channel instead of using both. And this is a little more in-depth of what we added to the knock block DDC. Originally, it just has the DDC and its control signals. We added in a decimation block that decimates the sync signal and makes sure that it keeps its timing alignment with the IQ data. And then there's some buffering that will make sure that channel 1 and channel 0, their data stays in sync and is continuous. And then there's just the packager that does the bit manipulation to put everything into 32 bits. And now Ron's going to talk about the compressed sensing.
So now that we have the synchronized, the sync signal coming in through the EDIS X310, now we can take that incoming time series and actually perform the support recovery to get the signals, to see what frequency bins have signals. So we have 2 flow graphs here, one to show how we perform the signal support recovery, and the other flow graph was to show how we perform the bit error rate measurement across all the different channels, which is used by the machine learning based decision engine. So here we have the flow graph where we absorb in from the EDIS X310, and there's a number of custom out-of-tree modules, out-of-tree blocks that we built. So one of the first ones was the ability to extract this sync trigger or sync signal that was embedded by the X310 in the FPGA. So what we do is we extract that, and we take that time series, and we basically limit it. At the time when we were first implementing this flow graph, we weren't sure how fast we could process the OMP algorithm, so we needed a way to basically lower the duty cycle of the system. So the two large blocks that you see, those are outer tree blocks. The first one on the left side performs the branch expansion. So Matt mentioned that depending on the number of signals we're trying to detect, we need M measurements. So you see M different measurements coming out of that block. So essentially that branch expansion is just a large channelizer. So all that data, as it gets channelized, gets run into the OMP block. This is running the orthogonal matching pursuit algorithm, as Matt mentioned before, to recover the supports. Ultimately, the output of that is a vector of instantaneously detected bins that have signals in them, which is output to the MLBDE. So this next flow graph is showing how we send a pseudo random bit sequence across all the different available frequency bins, and we're measuring essentially the bit error rate, which is going to be used to assist the MLBDE's determination of an optimal frequency bin. So MLBDE, there's a lot going on in this graph, but essentially it takes over a UDP socket, it takes two sets of information from the previous flow graph, which is ultimately the instantaneous vector of which frequency bins have signals, as well as the bit error rates for all the available frequency bins. So MLBDE takes this information to generate the optimal, or calculate the optimal bin to use as a transmission frequency. And so two of the goals are to basically pick a frequency bin that is robust and high performing, meaning something that doesn't have to be changed all the time, and something that has a good bit error rate. And so there were a number of different heuristics that were evaluated as part of this machine learning based decision engine. So it was cast into a multi-arm bandit problem. Ultimately we ended up with the epoch-greedy heuristic that we use for the MLBDE, but all along there was a random policy that was also evaluated. So at any given time we could evaluate how well the heuristic would be performing against a random frequency selection bin. So the MLBDE software was validated against 4 different scenarios just to see how robust it was in performance. So the epoch-greedy heuristic that was chosen was evaluated against a random policy. We also needed to verify that the MLBDE could process data fast enough that it could handle how fast it would be coming out of the OMP algorithm. And the third test was to validate the importance of the interference side information. So essentially the instantaneous vector of signals that was detected, and we noted that there was a good benefit from using that information as calculating an optimal frequency bin. And also there's a compound metric used to actually select the bin. So it's not just the pure reward metric, it's actually, we're using the bit error rate as well as the instantaneous signal, the signal interference vector.
So we simulated the whole system using basically what you see here. So we used one EDIS-X300, a B200, some custom PCBs that house the DSIC, and an environment emulator where we had 2 Keysight signal generators emulating frequency hopping radios. And here we could see a short demo. There's another demo that I could show at the end. This is just showing the whole system. If you look in the upper right corner, and I have another one. It's hard to see with this one, but you could see the green line is moving around. The red is the instantaneous jammer detects. The green is the output of the MLBDE. And at the end, I have another video that it'll look a little bit more obvious. This is a description of what you'll see. So this is the system GUI. The top right is the burr output of our burr calculation engine. Bottom right is the instantaneous jammer count coming from our orthogonal matching pursuit compressed sensing recovery engine. The MLBDE is in green, so all the data gets sent to the MLBDE, which comes up with the optimal choice, optimal new channel to select. And the bottom left is the a waterfall detects versus time. So future sensor work. So this EMEA sensor actually builds on a family of what we call analog information converters starting back in 2015. We started with just frequency domain sensing. We built a few chips doing that. And then the DSIC was actually a dual domain sensor where it could do sensing in the direction of arrival domain, sensing in the angular domain, so finding the direction of arrival, as well as spectrum sensing. So just before we get to the short video, conclusions. So a CS-based receiver architecture can sense the RF spectrum in a fraction of the time as a current state-of-the-art techniques. So the current state-of-the-art techniques are all take about n amount of operations or n samples, whereas we only need m, where m is equal to k C0 log n over k number of compressed sensing measurements. We built a proof of concept called the ITRN, which you saw and we'll see in the demo video next. The jammer location coming from the EMEA sensor is sent to the MLBDE, and the MLBDE makes an optimal corrected decision, which is then sent to the ITRN transceiver. Currently, we're doing some benchmarking of the ITRN and comparing against other EMEA sensing architectures. So far, the results look like it is following the theory. So whereas an FFT-based or sweeping spectrum sensor-based EMEA sensor will take, requires n number of samples, we only require m. So here's our references, and then I have a short video which I'll bring up. Oh, that's not it. Right, so you can see here, this is across 500 megahertz we're scanning, and we have two frequency hopping radios centered at just offset from the center, and they're 66 megahertz wide each. And we're moving them around, and you can see that as we move them, they're being detected. So in the bottom right, you can see the EMEA sensor is detecting the frequency hopping radios. And you can see in the upper right, this is maybe not the best example, but typically every couple seconds, or maybe on the order of 30 seconds, we're doing 500 megahertz. We're calculating the burr for each of the channels with an outstation. And you could see the green MLBDE output in the upper left jumping around trying to find the most optimal, well, it is finding the most optimal new channel to tune to. So that's it. Thank you.
Thank you. Are there questions? I have a question. How long did you measure the latency it takes between your measurement until you have your what's it called, your processing finished?
Yeah, we're still calculating that now. But yeah, do you want to talk a little bit about that? Yeah. So we're still working on that now. I mean, what about duty cycle or anything? You have those numbers off the top. I don't have the numbers off the top of our head. We're going through the characterization of things like that right now. So we don't exactly have a latency yet. So I could maybe on the order of magnitude of milliseconds, maybe latency so far.
All right, thanks. Well, we have time for more questions. And if there are questions online, please tell me.
Hi, really interesting. Orthogonal matching pursuit is a pretty compute-intensive algorithm. Do you see any limits as to bandwidth or performance from that?
Yeah, so we encountered that same problem. So early on, in the video that you see, actually our duty cycle is pretty low. It's probably about a little bit less than 2%. So what we tried to do was explore using a GPU to do some processing. Problem is the pseudo inverse is very hard to parallelize. But the nice thing about it is some of the processing that we can have, we can actually store as a lookup table. So for up to a certain number of signals, because of the amount of memory bandwidth that's available, we can actually store it as a lookup table. So that's one way to actually accelerate it, but we don't have the results of the timing or the performance improvement for that as we're currently implementing that. But yes, we did see that.
All
Yeah,
right.
Unfortunately, some of the benchmarks, we're right in the middle of calculating them right now, measuring them, calculating them. So it's still ongoing work.